Hello, my name is Connor Stone. I'm the lead developer of AstroPhot, and today I'm going to go through one of the AstroPhot tutorials with you to get an introduction to some of the features of AstroPhot. Our goals with this video are to learn the very basics of creating a target image in AstroPhot that represents your data, creating a model that is going to hopefully represent some object in the night sky, and then fitting that model to the data. Future videos will go over some of the more advanced features of AstroPhot to let you do other techniques to expand on that basic functionality, but this is the key stuff that you need to know to get started using AstroPhot. So let's dive right in. This is the Getting Started tutorial on AstroPhot. You can find it on the AstroPhot website. You can download the Jupyter Notebook and run it for yourself. I suggest you do because there's lots of detail in there that I'm going to skip over today as we go over just the basics. To begin with, we're going to import everything. We import AstroPhot as AP, so let's do that. And it takes a while, mostly because of the PyTorch import, but that's okay, because once it's done, we are ready to go. Okay, let's make our first model. Everything in AstroPhot pretty much is object-oriented, so we call AstroPhot model. We're going to make a model object. We pick the type. This is going to be a Sarsic galaxy model, basically a generalization of a Gaussian, and it's the classic thing to use for an extended object in the night sky. We give it some values for the parameters of that model, and we have to give it a target. Every model in AstroPhot needs a target, basically the image that it's supposed to be modeling. In this case, we create a dummy target object with just 100 by 100 zero pixels. So nothing really there in the data. We're all just focused on the model. The initialize function makes sure that everything is ready to go for that model. And then we print it and we get some information about the model that we've just created. First of all, the target image object has a world coordinate system, but since we didn't provide any information for the world coordinate system, it's basically just pixel coordinates, so units of one. And then we've got our initial values that we set for all of those parameters. We can plot the model using a built-in method in AstroPhot, plots model image, pass it the model, and boom, that's what our model looks like, projected into the pixels of that dummy image that we created. Keep in mind that every model in AstroPhot is actually an infinitely smooth model that you can evaluate anywhere in the night sky. It's not always interesting anywhere in the night sky, but you can evaluate it at any coordinates. The model image function just evaluates it within the pixels of the target that we're looking at. So this is what it will look like projected into the target. Let's make this a little more interesting. So here we create a target image object. First, we've loaded in some data from a FITS file, and we set that as the data. In a target image object, you can also make a mask. Let's just do uh, a bunch of zeros with the same target data shape. So we do that, and now we've created a mask, except that this mask doesn't do anything. This mask just tells it that every pixel is okay. If you set some of the pixels to ones, then that is going to tell it to ignore those pixels. You also create a variance, and you should pass in the appropriate variance for the image that you're looking at. That's how you get your best fits. But since we didn't have a variance with this image, I've just called auto. AstroPhot does its best to estimate the variance. This is not scientifically accurate, so don't use it for your science, but it is useful for testing. You can also add in other metadata. So here we've got the pixel scale. That just tells it how big the pixels are. But it's going to default to assuming that these are aligned north-south pixels and with an RA-dec of 0, 0, which is not necessarily very accurate. So you can, for example, do WCS equals, and then give it an AstroPy WCS object. You can totally do that, give it an AstroPy WCS object, and it'll use those world coordinate systems to actually project exactly where those pixels are on the night sky. That's super useful for doing really realistic analysis. Another thing you can do is add a PSF. We don't have a PSF model here right now, but If we did like ones, I don't know, 3 by 3, well, now that's going to be a pretty blurry PSF. It's just a 3 by 3 grid of ones. But that gives us a PSF blurring model for our image. All right, we don't need those extra things. Right now, we're just making a basic target with some data. Kind of like with the model image, we can plot the target image, and there we go. That's the data that we're going to look at. Nice big galaxy, and we're going to try and in vain to represent it with a Sursic model. Okay, so now we've seen how to create a model. We've seen how to create a target image. Let's combine the two. We create a model object. Again, it's going to be just a Sursic galaxy model, but here we provide that new target that we've created with the data just above here. And notice that we don't provide any parameter values. AstroPhot is a little smart in this respect because when you call initialize, it's going to make sure that every parameter has a value. It's not necessarily going to be the optimal values, but it'll use some basic heuristics to get in the right ballpark. And sure enough, we've got a Sursic model here. And if we plot the residuals over here, you see red is where the data is brighter than the model, blue is where the model is brighter than the data. And because we've got a mix of red and blue right around the middle here, that tells us that we're in the right ballpark, but it's definitely not optimal yet. So next, we're going to try and fit the model. We've got our data, we've got our model, at least in starting parameters for our model. Now let's figure out the optimal parameters for the model. So we use the Levenberg-Marquardt fit algorithm. That's the primary algorithm that you'll probably use in AstroPhot. And you pass it the model. The model knows what data it's trying to fit, so you just pass the model, tell it to run the fit, and so it's going to run the Levenberg-Marquardt fit on the model that we created. It's got 7 dynamic parameters, which is true for any Sursic model, and it's got 490,000 pixels. And there we go. Uh, the model has finished fitting the data. We've got to the chi-squared per degree of freedom minimum, which ideally should be 1, but obviously that's not going to be the case here because there's much more structure in this image than our Sursic is going to be able to represent. So let's look at the model and the residuals again. Now it's looking a lot better. Our Sursic model has basically collected the global structure of this galaxy and left behind just the spiral arm structure that it never had a hope of fitting anyway. So our residuals look a lot better now. We've really recovered that large scale structure for the galaxy. We can plot because a Sursic model is a radial model, as in it's all represented by a function of radius along the major axis, and then just turned into elliptical isophotes. We've got our Sursic model, which is the blue line here, and then the orange points are increasingly large radii of isophotes, where we just take the median of the pixel values along those isophotes. And that lets us compare on a 1D profile data versus model, and it looks pretty good. Um, Now we've fit the optimal parameters, but we do want some uncertainty on those parameters. And so we update the uncertainty and we plot the covariance matrix, which gives us the uncertainty on each parameter. That's the Gaussians that you're seeing here. And then it also gives us the covariance between every parameter. Sometimes, actually quite often, parameters have a bit of covariance between each other. There's certainly a few here. And so having that represented in your uncertainty model can be quite important depending on what your downstream science is. You can also get the total flux and the total flux uncertainty from your model. Keep in mind, though, that the way AstroPhot works, because it's super general, it doesn't integrate out to infinity. It integrates the light within the window that you're doing your fitting. Um, so this is the flux within the fitting window. This is the total magnitude within the fitting window and the associated uncertainties. If you want it integrated out further, just make the window larger. You can replace the target image for a model with a bigger target image if that's what you need. Okay. Now, not every fits image is just cut out exactly the way you want it around the object that you're interested in. So you can provide a window when you create your model object, and that window just has the pixel values for the bounding box that you're interested in. Imin, Imax, Jmin, Jmax. And so if we plot this, we're going to plot the target image and then a box over top of it. And this is the region that this new model we've just created is going to focus on. So it's only going to care about the pixels in here. And so if we run the fitter on that, boom, it's done. We've found the minimum chi-squared per degree of freedom. Notice that we're fitting on a lot fewer pixels now, and it moved pretty fast through that optimization. Here we go. There's our residuals. You can see that it found some decent starting parameters. It then optimized those parameters to get us some nice balanced residuals here. It looks like there's still some spiral structure left over in that little object in the corner there. So this is how you pick out a certain sub-region that you're interested in. Um, Also useful to keep track of is the actual metadata for all of your parameters. So we created a Sursic model, which means that all of the Sursic parameters, like the effective radius, become attributes of that model. And then we can query all sorts of different metadata for them. The units, in this case, arcseconds, because it's a radius. The shape, this open close brackets just means it's a scalar value, a single number. Uh, you notice how the center is a vector of length 2 because it's the x and y coordinates. Dynamic tells us if the model is actually going to be modified in the optimization procedure. If it's false for dynamic, then that means AstroPhot is going to leave it fixed. It's never going to change that number during the optimization procedure. Sometimes you want to turn parameters off and on in order to get a more stable fit, just depending on your scenario. And then a description. Every model parameter has a little description. Here it says half-light radius, also called effective radius. That's useful if you didn't know that RE was the short form for effective radius. This will let you know. That way you can just keep track of what's going on in all of your parameters. You can change a model parameter between dynamic and static. So changing RE to static, now that means it won't change when you run your Levenberg-Marquardt fitter. And to dynamic means it will change when you run your Levenberg-Marquardt fitter. You can also do this for a whole model at a time, and it'll do that to all of its parameters. You can set constraints for individual parameters. So here the axis ratio is set to a constraint between 0.4 and 0.6. So AstroPhot will respect that boundary and it won't let the parameters explore outside that range of parameter space. That can be really useful for getting rid of multiple modes and where you know which one you're interested in. You can also set two parameters to track each other. So here we've got the position angle for model 2 is going to be fixed to match the same value as the position angle for model 1. That's more useful later when we get into group models. You can save the parameter values to an HDF5 file and then load them back in at a later time. You can save your model image. So you take your model, if you call it like a function, then it's going to return a model image. It's kind of like the target image object, except it's intended to hold on to a model image. And you can save that right to a fits file and then load it back in. You can actually access the data from a model image very easily, just call .data and then you've got it. But here we have access to the pixels from our optimized model. Um, and here we go. There's various parameters that you can send into the model image function. This one changes the number of uh, levels for the color map, which can be helpful for finding certain types of structure. The target images as well, you can save those to a fit file and then load them back in right from the constructor of the target image. Just give it the fits file and you're off to the races. There's some other variations you can do. So this one here, we've created a model image, grab the data, turn it into a NumPy array because it comes out as PyTorch, since right now we're doing the PyTorch version of AstroPhot. It'll come out as a tensor, but we want it as NumPy so we can plot it. If you want, like I said earlier, you can just pass a world coordinate system right into AstroPhot when you're creating a target image, and it will make sure that that target image respects the world coordinate system that you've given it. Or even better, just load right from a FITS file. As long as that FITS file has the appropriate keywords for the standard world coordinate system, just a tangent plane, then AstroPhot will read in those keys and um, create the appropriate world coordinate system internally, so you don't have to do it at all. You just pass in the FITS file and it's ready to go. There's some other things that I'm not going to get into too much detail here. You can list out all of the models that AstroPhot has of a given type. You can change between uh, GPU and CPU. You can also change between float 32 and float 64, and AstroPhot will just make sure everything uses float 32 or float 64. And you can also set the way that AstroPhot does output. So this first message only goes to a log file, so you don't see it pop up here. This second message does go to the console, but only the console. And this third message goes to both. And so that way, you can control how AstroPhot outputs its various messages to the console. This whole tutorial was in the PyTorch mode. There's an equivalent tutorial in JAX. Everything is identical. It works out exactly the same way, except you can run everything where all of the numerical calculations are done in JAX. That can be useful depending on what framework you're doing for the rest of your analysis. AstroPhot can merge in well, whether you're using PyTorch or JAX. In order to use the JAX version, the best way is to just set an environment variable called Cascade Backend, set it to JAX, and you're ready to go. Another option at the very, very top of your file, just set backend.backend to JAX, and that'll do the same thing. It'll tell AstroPhot to switch everything over. All of its numerical backends, those will use JAX from that point on. All right. So that concludes our first tutorial. We've just covered the real basics of getting your ideas into AstroPhot. So you create a target, you put some data into that target, you put your mask, your variance image, your world coordinate system, your PSF into that image, and that represents the data that you've collected with your telescope. You then create a model object, make it have a certain model type, like a Sursic galaxy model. You give it that target so it knows what it's trying to fit, and it should be able to get itself started. And then with a fitter like the Levenberg-Marquardt fitter, you should be able to get really decent parameters for your model very quickly. So this is all you need to get started with AstroPhot. There's going to be future videos, and those will get into some of the more advanced features that AstroPhot has access to expand on this basic fitting concept. I hope you check those out, and definitely contact me if you have any questions about AstroPhot. With that, I think that's the end of the video. Bye.